As we begin section 9.3, we're talking about rational functions. We're going to focus on three major words today: discontinuities, vertical asymptotes, and wholes. And as we start, we want to kind of review the idea of what a rational function is. And very simply, as you remember, it's two functions where you have a numerator function and a denominator function, and they are both polynomials potentially, and the denominator can't be equal to 0. So, functions and terms to know for today. We're going to focus on the idea of what a point of discontinuity is. A point of discontinuity is just what we've written here. A is a real number, and we're going to highlight the word real number because that word real number is going to be key later, for which the denominator of a rational function f is 0. And then a is not in the domain of f. In other words, a cannot be an input of f for that. As a result, we call this function f not continuous at x equals a. Also, therefore, the function has a point of discontinuity at x equals a. Now, if you're pretty normal, then you're going to be kind of saying, what are you saying? Well, basically, I want us to find the values that are real numbers. Find the values that are real numbers that make or that cause the denominator to equal 0. That cause the denominator to equal 0. Okay? So all that means to say we're looking to figure out, when we look at the denominator and focus on that, what will cause that denominator to equal to 0. Now we may have to factor it, we may have to take things out or GCFs or things like that, but that is the main idea of what a point of discontinuity is. So let's take a look at example 1 and let's find the points of discontinuity. Really very straightforward. We're going to look at the problem and we're going to factor the top, obviously take a 2 out of the top. We're going to factor the bottom and take an x out of the bottom. So now in the denominator we have two parts. We have x equals 0 and x plus 5 equals 0. So if x equals either 0 or negative 5, either one of these will cause points of discontinuity, because if you would plug those numbers back into the original problem, you would get values in the denominator that were equal to 0. Let's go over here and look at b. If we take a 4 out of the numerator, we get 2 minus x. In the denominator, hopefully you can very quickly remember that's going to be a plus and a minus, an x and an x. Well, that's going to be a minus 6 and a plus 2, because that gets us negative 4x in the middle term. So our points of discontinuity are going to occur when x plus 2 equals 0 and x minus 6 equals 0. So that happens at negative 2 and positive 6. So those are our points of discontinuity. Now in each of these two cases, they're very simple, straightforward. One's a GCF factor, one is just a factoring of a polynomial. But in either case, if you plugged in your denominators back into your original function, your denominator would be undefined, and that is called a point of discontinuity. Now, on Wednesday, we're going to be looking at graphs of this, but for today, we're just going to be focused on the actual points of discontinuity. These points can be broken up into two different terms. They might be referred to as wholes, or they might be referred to as vertical asymptotes. We've done vertical asymptotes already with our basic inverse variation, but let's talk about what it means to be a whole. If the factors cancel, then that point, that value of x equals a, is called a whole. So that you have the factor x minus a, and then the whole would be x equals a. Now, that means under the simple condition, okay, that provided that the number a is a real number, and we need to make sure that we're talking real numbers, not imaginary numbers. And then a vertical asymptote occurs if the factor doesn't cancel, and the denominator would then be equal to 0. And once again, imaginary numbers are not going to be points of discontinuity. So let's look at a couple of these examples below. Example 2. Here we have it already factored, and so it's very simple to see. Nothing cancels on this problem a. So you have a denominator of x minus 3 equals 0, and another denominator being x plus 4 equals 0. So you have x equals 3 and x equals negative 4. Both of these are going to be vertical asymptotes. okay? Because both of these are places where the denominator does not factor. We don't have any holes because nothing canceled. On letter B, we have two denominators, x minus 2 equals 0 and x plus 2 equals 0. Well, x minus 2 obviously is x equals 2, and x plus 2 is going to be x equals negative 2. So we have two places where we have points of discontinuity. I'm sure you've seen already that the x plus 2's, though, are the same in both the numerator and denominator. So the x equals negative 2 value that we have right here, this part is going to be then described as a hole in the graph. But the other part, x equals positive 2, is going to be described, therefore, as a vertical asymptote. Okay, let's move down to letter C. The numerator we have is x squared minus 1. I'm sure you're realizing that's x minus 1 times x plus 1. Those are conjugates. In the denominator, we have x, x plus 1, and x minus 5. I'm going to right away realize, hey, those x plus 1s are going to cancel. So when we get our answer for x plus 1, we're going to have to realize that that's a whole. So let's look at our three parts. X equals 0, x equals negative 1, and x equals 5. Okay, x equals 0, vertical asymptote. X equals negative 1 is going to be a whole. And lastly, x equals 5 is secondly another vertical asymptote. So I'll circle our vertical asymptotes in blue, and circle my hole in magenta, and there are our three answers. Let's take a look at D. Doesn't look like the numerator factors, and it also doesn't look like the denominator factors. And so our problem really is just going to stay the same. Let's take that denominator and set it equal to 0. X squared plus 9 equals 0. That gives me x squared equals negative 9. So I take the square root of both sides, and I'm going to get plus or minus 3i. Well, plus or minus 3i are imaginary numbers. These are not real numbers. So this graph has no vertical asymptotes, and it also has no holes. So this graph would be called a continuous function versus a graph that's a discontinuous function. And that's the idea behind what we're talking about. The idea of discontinuities means that you would not be able to draw a graph without picking up your pen or picking up your pencil. So we've got a little bit of a challenge for you as we go down to the bottom page. I have three puzzles here, and your goal with these three puzzles is to try to draw them in such a way that you would not lift up your pen but still be able to trace over the entire puzzle. Encourage you to try this, see if all three of these are possible, or maybe one of them is actually impossible to do, but that's going to be your challenge as well as you work through this. So this is the idea of continuous ideas versus our main idea today in understanding algebraic ideas of discontinuous functions. I hope this has been helpful in understanding this material.